All right, let's head out on an investigation. We're going 33,900 light years from home to a place called Messier 3. Now, imagine a vast, ancient city, just jam-packed with 500,000 stars. It's an incredible place, a hub for some of the most extreme physics in the universe, but it's also hiding some serious mysteries. Today, we're going on the hunt, trying to track down the secret partners of some of the strangest objects you can imagine.
So let's just think about that for a second. The challenge here is, well, it's immense. In a stellar metropolis as crowded as M3, finding one specific, super faint companion star right next to its incredibly dense partner, it's like trying to find one particular firefly in a city that's already blazing with spotlights. So really, how on earth do astronomers even begin to crack a case like this?
Well, the objects of our search are the companions to these things, millisecond pulsars, and they are wild. Think of them as the spinning corpses of giant stars. So the star dies, but then a nearby companion star starts feeding it material. This cosmic snack actually recycles the dead star, spinning it up to insane speeds. We're talking hundreds of times every single second. But here's the thing. The key to really understanding the pulsar is often finding that companion that did the recycling in the first place. Okay, so our whole investigation is taking place in one very specific location. We're zooming right into the globular cluster M3, and we're setting the stage to find these amazing cosmic lighthouses, and hopefully their very elusive partners. Globular clusters like M3 are the absolute perfect hunting grounds for this kind of work. I mean, the stars here are packed in so tightly that all sorts of weird stuff happens. Binary systems form, stars get way too close to each other, and these exotic objects like millisecond pulsars are created at a rate 1,000 times higher than in the rest of our galaxy. It's basically the perfect laboratory for putting our theories of stellar evolution to the test.
So how do you actually conduct an investigation on a cosmic scale? Well, just like any good detective, you need a very specialized toolkit. So let's break down the methods these astronomers used. Here's the 4-step game plan. First up, you use these giant radio telescopes to get an incredibly precise position for the pulsar. Think of it as its cosmic GPS coordinates. Step 2, you bring in the big guns, the Hubble Space Telescope. You get it to take these super deep, detailed photos of that exact spot, basically your crime scene photos. Third, you take any star you find there and put it on this special chart called a color magnitude diagram. This thing acts like a police lineup for stars. And finally, you compare your suspect's profile against theoretical models to see if you've got a match. And you know what? That toolkit, it totally works. The investigation got results, so now we can start opening up the case files on the pulsars, where a companion was successfully identified. First up, let's open case file M3B. In these Hubble images, right where the radio telescopes told us to look, you can see it marked by that magenta cross, we find our first suspect. It's a faint blue object. This is our first piece of hard evidence, a visual confirmation right at the scene of the crime. And this is how we confirm our suspect's identity. See on the left? That's our lineup, a chart of all the stars in the area. And our suspect, marked by that orange square, it really stands out. When we compare its position to our models over on the right, it's a perfect match for a very specific type of star, a helium white dwarf, with a mass just about 18% of our own sun. Case closed on M3B. All right, next up is case file M3D. And again, a faint blue companion is found right at the pulsar's location. But this one's a little trickier. Its properties don't give us one single clean identity. The evidence kind of points in two different directions, and that presents the detectives with a real puzzle. So here's the dilemma. The data points to two totally different possibilities. There's the young solution, which suggests a heavier star, about a third of our sun's mass, that cooled down really fast and is only about 300 million years old. But then there's the old solution, which points to a lighter star that cooled down much, much more slowly and is nearly 4 billion years old. And because these measurements are pushing the absolute limits of what Hubble can even see, both possibilities actually fit the evidence. And believe it or not, the story pretty much repeats itself with our third success, M3A-F. We find the companion, another faint blue star. But just like with M3D, the data is a bit fuzzy, and it gives us two possible answers. It could be a younger, more massive white dwarf, or it could be an older, less massive one. So the key takeaway here is, while we've definitely found the suspects, their exact life stories are still a little bit hidden from us.
But what about the cases that weren't so easy to solve? In detective work, a missing body or an empty crime scene can sometimes be just as informative. So let's look at the pulsars where no companion was found. So this is the location of M3A, which is a type of pulsar known as a black widow. And as you can plainly see, the scene is empty. There is no visible companion. But this is not a dead end. The absence of a star tells us something really important. It sets a limit on just how faint, and therefore how small, the companion must be. Even an empty frame gives us a crucial clue.
Okay, now get ready for a real plot twist with pulsar M3E. Back in 2006, a faint red object was spotted super close to the pulsar's position. But now, look at the image from 2021. The object has moved. So is this our companion? Or is something else going on here? That 15-year gap between the photos is about to give us a definitive alibi. And here it is. This is the smoking gun. This diagram is basically a traffic map of the stars in the area. The real members of the M3 cluster are all moving together. They're all bunched up there in the center. But our suspect, that red dot, is speeding off in a completely different direction. It's not part of the M3 cluster at all. It was just a foreground star passing through the crime scene. We have an imposter. Unmasking this imposter is actually a huge win for the investigation. It gets rid of a false lead, it cleans up the case file, and it lets astronomers focus their search for the real companion, which must be even fainter and even better hidden than we thought. Proving what something isn't is such a critical part of doing science.
So, after all this detective work of finding some suspects, hitting dead ends with others, and even unmasking an imposter, what's the big takeaway? Why does solving these stellar mysteries even matter?
The researchers themselves put it perfectly. The real power here is in combining different techniques. It's that synergy, that teamwork between radio telescopes giving the precise coordinates and the Hubble Space Telescope providing the deep visual evidence. That's what makes these discoveries possible. No single instrument could have cracked these cases alone.
So, what's the final verdict? Well, this investigation proves that by combining the sharp eyes of Hubble with the keen ears of radio telescopes, we can solve mysteries that were once flat out impossible. We've confirmed the identities of 3 companions, which shows our theories of stellar evolution are on the right track. And for the 2 that got away, well, we now have a much smaller, much fainter place to keep searching. This is exactly how science moves forward, by piecing together clues from the most extreme crime scenes in the entire universe. So, the investigation has closed 3 cases, but it's left 2 of them tantalizingly open. And it just makes you wonder, in that dense, ancient city of stars, with mysteries still unsolved and suspects still out there, what other secrets is M3 just waiting to reveal?